This is 3.8 representation of solutions. Our outcome is I can use particulate models to represent interactions between components and concentrations of components in a mixture. So AP exam is big on particulate models because you really have to understand the forces and the interactions that are at play in order to draw them. So particulate models can be used for representing interactions between components of a mixture. So things like ion sizes, the orientation of solute and solvent particles. We can also see intermolecular forces. And then we can also use it to represent concentrations, especially relative concentrations. So 1, justify the orientation of water molecules. So the partial positive end of water is going to be attracted to the negative chloride ions, whereas the partial negative end of water, which is the oxygen side, is going to be attracted to positive sodium ions. This is a Coulombic attraction that's occurring in this solution. So why is the chloride ion larger than the sodium ion? So sodium has lost its valence electron in its third shell, whereas chloride still has all 3 of its shells. So why do we see 1 sodium ion for each chloride ion? Because that's the ratio present in the solid salt crystal. So when we write the formula of a salt, we write it as if it's 1 sodium and 1 chloride, but in reality it's a big network of those ions. So we have one of those ionic crystals. When salt is added to water, we have boiling point elevation that occurs. So explain why using this diagram and intermolecular forces. So the addition of these sodium and chloride ions allows a new intermolecular force to occur. So we have this ion dipole attraction that's going on. So over the entire volume of the solution, that little tiny additional force kind of adds up. So we're going to need a lot more energy to boil the water to overcome these newly formed forces. In this diagram, we need to show a lot of things. We need to show reaction stoichiometry, limiting and excess reactants. We also need to make sure that we show correct ion size as well. So in this reaction, we're going to have excess chloride. So there's only 4 Ag plus ions to start. So that means I can only react with 4 Cl minus ions. So those unreacted excess Cl minus ions will still be floating around in the water along with our spectator ions. These are the ones that remain aqueous after the reaction has occurred. They don't actually react together. Next, we want to draw a diagram that shows the arrangement of water molecules around a nitrate ion and a magnesium ion. So if we were to add magnesium nitrate to water, we would have twice as many nitrates as magnesiums, and the water molecules would orient themselves so that the positive poles of water face negative ions, and the negative poles of water face positive ions. So here was a question from your summer assignment quiz. So the diagram below shows a 1 liter solution of sugar dissolved in water. The dots represent sugar molecules. So to simplify the diagram, we didn't add any water molecules. We just see the sugar particles. So which best reflects the sample once we add an additional 1 liter of distilled water? So we're doubling the volume here, but we still have the same number of moles present. So I need a picture that's going to show me half the concentration. So that's going to be picture B here. So what information about a solution can be shown with a particulate diagram? We can see intermolecular forces, we can see relative concentrations, We can see interactions between solute and solvent. We can see ion sizes, the orientation of these particles, and of course also concentration as well.